Thank you very much. I apologize.
Also, Dr. John Spadina, let me know.
Okay. I apologize to all of you for being late, but I thank Matthew for his perfect introduction. So I'm skipping all the elementary details. Okay, we have the partitions, we have the overpartitions, and I have one objection here. At least in the context of Gordon identities and their extension to overpartitions, we consider, we overline the last occurrence of any part, not the first one. The definition for overpartitions stipulate that we overline the first occurrence, but for Rogers-Ramanujan Gordon identities, we overline the last occurrence.
And you get the same enumeration, huh? You get the same enumeration.
You get the same enumeration, yes. I mean, there are other characterizations also. Okay, so we have Euler's theorem. And Matthew told you about generating functions also, which enumerates partitions where parts don't, multiple parts are not used, parts occur in singles only. In other words, frequencies are less than, strictly less than 2. This is the same thing as partitions of n into parts that are in some congruence class. Condition. And I'm not going to write the congruence condition. We have odd parts there. Therefore, once we have parts that come from certain congruence classes, we have a generating function that's a single infinite product. And then we fast forward. We have Rogers-Ramanujan theorems. Say Rogers-Ramanujan 1, where we have partitions into parts that are distinct and non-consecutive. So we have to consider consecutive frequencies that I plus 1 is less than 2. Again, this corresponds to partitions per this theorem, where we have certain congruence conditions also. Again, the generating function is a single infinite product. And then we fast forward 40 plus years. We have Rogers-Ramanujan Gordon, where he replaced this two by a larger number. I plus 1 is less than or equal to k, and we have to bound the number of occurrences of 1 also. You get 1, you get all. Again, this corresponds to partitions of n into parts that satisfy certain congruence conditions. Again, the generating function is a single infinite product. And of course, we have the overpartition analogs for these theorems. Do we have color chart?
If you take a look at, then there's more in that cardboard box.
Oh, very good. Okay, I prefer yellow. Then we have overpartition analogs. For Rogers-Ramanujan Gordon, the condition for consecutive frequencies adding up to less than k, this time we have f of I plus f of I bar plus f of I plus 1 strictly less than k, and again there's a bound for the number of occurrences of 1. We still get congruence condition for both the parts and for the overlying parts equals, these are overpartitions. Let me represent them this way. Again, parts that come from certain congruous classes. We still have a single infinite product. At this point, I need to say something about these congruence conditions. These congruence conditions are, in Gordon's theorem, are modulo 2k plus 1. And for overpartitions, they are, I think they were 2k. But similar results for overpartitions come after the...
But only Ramanujan has two congruences. Is only one in Gordon? We have two.
We have a single congruence condition here.
So Gordon is not...
Cannot be 0 or plus minus a, modulo 2k plus
Oh, okay.
1. Yes.
Oh.
I still count this as a single congruence condition. I mean, because the modulus is only 1.
Alright. Oh, but in this case, that's slip forbidden. And in the Ramanujan, you have also slip forbidden. So it's a direct... So it's Ramanujan is a special case of Gordon?
That is correct. When you take
in case 2?
k equals 2, then
yeah, exactly.
you get Ramanujan. For a equals 2, that's Ramanujan 1. For a equals 1, that's Ramanujan 2. Yes, that's a spatial case. Yes, and this is modulo 5. Yes. Parts cannot be 0 or plus minus 2 modulo. I don't want to state these explicitly because I'd like to focus on these conditions today and how to write bivariate generating functions. But a natural open question after Gordon's theorem is to get a similar partition identity containing even modulus here. So an open question afterwards. Can we do this? Can we get a similar identity for even modulus? And a partial answer was given by George Andrews. I don't remember the exact year, in the 70s. And he did the modulo 4k plus 2, no, 4k plus 2. And then a full answer was provided by David Bressoud. A full answer, I say. That is 1980, 1981, 1979, thereabouts.
So sure is a special case. So watch 6? No. That's something that...
Schur's theorem considers frequencies of 3 consecutive parts, fi plus 1, fi plus 2. At the end, if I have time, I will say that these methods don't pertain to Schur's theorem. That's still ongoing research. Okay, so Bressoud's theorem, he has many, but his theorem in this context says that if we take partitions, regular partitions of integers, where we have Gordon's condition, fi plus 1 less than k, if 1 is less than a, on top of this, he has this extra condition in Cortel and Lovejoy's terminology, when these frequencies are saturated, meaning they attain their upper bound, if pi plus 1 is equal to k minus 1, then the sum of all those parts, I times fi, sum of all i's plus sum of all I plus 1's, must be congruent to a minus 1 modulo 2. That's Bressoud's extra condition. If this is satisfied, then this is the same thing as partitions of n into into parts that are in certain congruous classes. And they are modulo 2k, yes. I think that's modulo 2k. And again, once you have congruence conditions into a single modulus, you have a single infinite product as the generating function. And of course, there was an overpartition analog of Bressoud's theorem. Number of overpartitions satisfying this condition, let's say condition 1, plus, if this sum is saturated, if I plus I plus 1, no, if I bar plus I plus 1 is k minus 1, then the sum of all these parts, sum of I, sum of overlined I, and sum of I plus 1s, congruent to a minus 1 plus b of I modulo 2.
But the FII overline is either 0 or 1, right?
That is correct,
Yeah.
yes. This is either, oh, excuse me, this is I bar. This is 0 or 1. That is correct, yes. Other frequencies are, they have more freedom, but for overlying parts, either 0 or 1.
Are there other generalizations in which you can have more than 1 bar per?
That's still ongoing research. That's part of the research, but the main difficulty is we don't have such nice generating functions. Either we cannot generate the series, or they are not fit for Jacobi's triple product identity. That's the bottleneck. Okay, and again, this equals number of overpartitions of M into certain congruous classes. Congruous conditions. And then the generating function is still an infinite product. Still a single infinite product. And overpartition analog of Bressoud's theorem is a theorem of many authors. Two cases, two extreme cases, if I'm not mistaken, the A equals 1 case and A equals K case is done by Cortell, Lovejoy, and Malay, I think. And the remaining cases are done by Bill Chen and, I'm sorry, I cannot remember all the names, but Bill Chen and collaborators.
I think it's Sang and Shi for that.
Is she? Okay. Okay, now this is one checkpoint in talk. Any questions? Okay. So the proofs to all theorems I listed so far, or Matthew listed so far. Go as follows. We have a class of partitions. And in this context, class of partitions satisfying Gordon's condition plus some other conditions. From these class of partitions, you write enumerants. This K and A, they are the indices you see over there. They are the variables you see over there. N is the number you are partitioning, which is called the weight of the partition, and M is the number of parts. Consider such enumerants. If I have time in the end, I will give you a concrete example, and find recurrence relations between these enumerants. Of course, you have to provide some base cases also, initial conditions, because these recurrences allow you to decrease M and N. So once you know what happens when M is 0 or M is negative, N is 0, N is negative, those are your initial cases. With that, your enumerants are uniquely determined. Once you have this, these imply functional equations plus initial conditions for the generating functions. What are the generating functions? They are bivariate generating functions for enumerant Q to N. That's the traditional choice of variables here. Exponent of x keeps track of which parts we use. Exponent of q keeps track of which number we are partitioning. So we have functional equations and initial conditions for these generating functions. That will give you one way to determine these generating functions uniquely. This is one line of computation. The other line of computation is you take a series that appear in literature, and for all theorems, I mean all theorems I've listed so far, they are variants or some twists of Andrews J function. Apply a change of variables if necessary, or multiplied by some infinite products. And get the functional equation satisfied by these series also. You have explicit formulas for these series. On the one hand, you just have the definition of this generating function. On the other hand, you have explicit formulas for these series. Because you have the explicit formulas, you can know which functional equations are and which initial conditions are necessary. And at the end, you argue that if you are lucky enough, you argue that because you have the same functional equations and same initial conditions, these must be identical. If they are the same, the functional equations and the initial conditions, you know that the generating functions are given by these series. And then the proofs, called apply Jacobi's triple product identity, to get the single infinite products, and that's it. So this is one answer to the open question after Gordon's theorem. Can we do this for even moduli? Yes, we can. And we can get over-partition analogs also.
So the proof is similar to overpartition?
Yes. We have the twist of J function, and then we have similar functional equations for overpartitions also. I think we have two terms on the left-hand side because we have to consider when you have an overlined one and when you don't have an overlined one.
So it's more complicated. A little bit.
Just a little bit, not too difficult. I mean, that will give you only one more infinite product to multiply the series. After Bressoud's theorem, naturally, one must wonder if we can replace this modulo 2 by modulo larger numbers. And the answer is yes for partitions. And we still don't know if we can do this for overpartitions. So we can replace this modulo 2 condition by something else. There's something I swept under the rug. I didn't tell you about this view of I statistic of Cortel and Lovejoy. That view of I statistic is the number of overlying parts that are less than or equal to I. Now I'll tell you about the proof strategy that will unify all the results we set up to here. Although we couldn't get the theorem for overpartition, we saw that we have to replace this view of I statistic by something else. This has to be replaced by, say, rho of I, which is a weighted sum of these overlying parts, or weighted count of these overlying parts. That's number of overlying parts less than or equal to I, number of even overlying parts less than or equal to I, minus number of odd overlying parts less than or equal to I. Of course, when you consider Bressoud's theorem for regular partitions or overpartitions, this makes no difference because it's modulo 2. Plus and minus is the same. But if you want to generalize this for larger modulus, we have to replace the definition of E by that. We did replace the definition, but we couldn't get the theorem in the end. I'll tell you why. This is another checkpoint. Any questions here? Okay, so the proofs to all these are essentially verifications. Now I'll propose you a new method, which will take only Gordon's theorem as a black box and construct all the remaining theorems. Assuming, or let's say, elaborate on the proof of Gordon's theorem by Andrews. So assume that the generating functions are of the following sort. A series, an infinite series where n is greater than or equal to 0, alpha of n depending on x times m of alpha plus beta sub n of x plus m of beta and so on, zeta n of x times m of zeta. For these alpha, beta, gamma, these are hypergeometric terms. Well, basic hypergeometric terms that don't depend on A. And these m's are monomials that do depend on A. Once you make this distinction, you argue that in the functional equations, alphas produce you betas, betas produce you gammas, gammas produce you deltas, and so on. In the end, the circle is complete, so you have finite limited types of terms. Once you assume that the series have this form, you can construct all generating functions from scratch.
But how many terms do you have? From alpha to...
That's part of the algorithm also. You try one
Oh, you
type
keep
of
trying.
term, two type of terms, three type of terms.
But
That's part of the experimental
Okay.
part. Yes, yes.
So that's a template for trying to find...
That's a template, exactly, exactly. So we can construct all series, and so far, one type of term didn't produce us anything. Two types of terms produced all the theorems you've seen so far. 3, 5, 7 types of terms imply only one type of term. So if you have odd number of type of terms, that automatically implies only one type of term. And 4, 6, 8, I didn't try 6 and 8, but I did try 4. It just gave you the dissections of the case when you had two terms. So the two terms is the key. And in extending Bressoud's theorem, modulo D, I had the series first, I have to admit, and I try to fit a definition to that series. That's how things work. But the bottom line is, you can produce series from scratch, but it takes a long time. So I need some computer help, because if you try something like Bressoud's theorem extension or Andrew's parity results extensions, computations may take up to days or weeks.
By hand.
By hand, yes. And these computations don't require creativity, therefore I need some computer help. I gave a similar talk when I didn't have this many results in Austria at risk. And they had some software to help me, but then there were some difficulties, so we couldn't collaborate. I'm giving this talk here also in the hope that we can have some collaborations in the near future. That's all I wanted to say. Thank you very much.